Okay. Okay, so just to make sure we're all in the right place, right? So hopefully you're here for the topic score. So so basically, like the idea of like the course is kind of like to discuss tensor networks, which are like a very convenient way to deal with tensors, and kind of like part of like what we'll be doing at the beginning of the course is just like kind of like to discuss what tensors are, like different ways in which they're used. By the way, here's my email just in case. You can feel always free to email me about if anything comes out. You can also call me Mariano, like, if you prefer, like over professor. Like I don't, I'm totally fine with those things. Like, again, if the projector were working, the first thing that I would do is kind of like just project the canvas side to kind of like show you what's on there. So basically what I was doing over the summer is like, I kind of like posted a bunch of papers on Canvas if you have seen it. Not that there are any expectations that you would even read them, like even like 10% of them. I just wanted to have like, like a nice compendium for you to access. Because if you scroll through them, I'm sure like everyone will see the works of titles that sound appealing, and others, they won't caught your attention. So it's kind of more like, kind of like think of it as kind of like as a future source. If for whatever reason, like after this class, you still want to keep learning more about tensor networks, then you can kind of like refer to those. And definitely there's some that are more useful and I'll follow more closely. But then basically what I'll do is like after a class tell you, okay, by the way, if you want to learn more details about this PDF has some extra information, and that like the PDF will be on Canvas, because like this is kind of like a somewhat recent topic, in terms of research and everything. So there are not, I mean, there are a couple of books, but you kind of have to, nothing like that would be well suited for like a class like this. So it's kind of like more relying on surveys and other things to kind of like go over the material, But I do think it's kind of like a nice topic just because it really does give you like an opportunity to connect different areas, like, and just kind of like to import ideas, like, either from physics into computer science, or computer science into physics, or like, mathematics, physics, computer science, et cetera, et cetera. So that's like, uh, during the first week, kind of like what I'll try to do is kind of like give like a broad idea of how some of the ideas are supposed to work. Now over time, we'll kind of like kind of like specialize on certain areas. Like the nice thing is like, because this is a topics course, we can really go in any direction that we want, which is why I kind of like created that Canvas poll. Just like letting you, that way you can tell me what your interests are. Like, for example, from the poll, I have learned, at least from everyone who completed it, that I think everyone has taken multivariable calculus. So that means that I can do multivariable calculus examples without feeling bad, like, so, which in the past, maybe I would have done it, but like I wouldn't necessarily have emphasized it as much now that I know that at least like the majority of you have taken it. But kind of like in terms of like how the course will be structured, like, there are no exams for the course. It is kind of like more like motivationally driven. So, you make out of it what you want. At least, I mean, there will definitely be some assignments that I expect you to complete, but, like some will be very interested in certain topics, in which in case I can give you guidance, like, I could put some problems which are specific to a particular topic, and then you can just complete those instead of others, if you're more interested in like the physics side or like the computer science side. Later on, like we will talk about, like PyTorch and like iTensor libraries and all these things, like of how you would actually run some of these programs. And again, like that might be interested more of interest to some, but others may want to focus more on the theoretical stuff. So I'll kind of like make it very flexible so you can kind of like pursue what you're really interested in learning. But yeah, like, there will be kind of like a minimum set of assignments for you to complete. But besides that, I'll kind of like be very, very open-minded on, how you want to like, specialize, like, so I'll kind of like we'll try to have like a bunch of examples of a bunch of different topics, and then you just like do, what you want. But yeah, again, like hopefully if by next time I have fixed the canvas, the projector side, I think with the computer podium, then I can show you a little bit like the canvas side, all this stuff. Is that okay? Making sense and all this, and then like I'll be around. I'll probably have my office hours after this class actually, and then if anyone wants to just chat to talk about more specifics, like I'm happy to do that. Once I hope to have decided the office hours thing like by this week, so I can also let you know about that. And so maybe just to kind of like get started, when you talk about, many of you probably have heard the like the word tensors before. The thing is like the word tensors is similar to kind of like the way the word work. You can say work in economics or work in physics. Like they can have like different meanings. Although like the word tensor is more like related. It's not as different as like in economics versus physics. But there is like a different understanding. Like if you come from like kind of like more like a machine learning or statistics perspective, there's kind of like a way. In which like the word tensor is understood, kind of like in machine learning. Or like more like maybe broadly statistics. And then like, of course, mathematicians have like their very precise definition of what you would like to call a tensor, right? So like, they're like the mathematicians. And then like, of course, like the physicists like also will use the word tensor. In some ways, like, in a sense, like these two are kind of like always the same, but they kind of like they will try to emphasize different aspects of the word tensor. So it's kind of like an interesting exercise to understand like all the different ways, like, in which that is connected to one another. Kind of what I was going to do, like what I wanted to do today, is kind of like more like the most down to earth version of how you would use the word tensor, right? Which is like, 99.5, like 90% accurate, and then you kind of like fix it a little bit to kind of like have like the perfect definition. But kind of like like if you have to do like the elevator pitch to someone like what is a tensor, like you want to summarize it in 3 minutes, and then this kind of what you would like to go with. Okay, so and so like in order to say that, like you actually want to do something similar for matrices and vectors, right? Like, so for example, if you wanted to say, okay, what is like a vector, right? Well, I guess I'll keep using the arrows, although soon like I'll forget about the arrows. But like typically if you just wanted to, maybe like the first way that you think of as a vector is some like kind of like a collection of numbers, right? Typically linear algebra into 50, right? Like you would put them as a column vector or a row vector. That doesn't really matter too much, but kind of like the important thing about a vector from this perspective is it has like it has like first element, a second element, and an nth element, right? Like the last one, and you can refer to them, like the components of the vector, like you can write the components of it as being like b sub I, right? So this is b1, b2, b3 up to bn. So I, here like it's taking the values. I goes from 1 to 3 up to n. And typically this is like referred to as the index, right? So the vector, what you would say is like a vector, like from this very down to earth perspective, like a vector is just whatever uses one index to specify, right? So like a vector has one index, or like needs one index, you know. Even before vectors, you could talk about scalars, right? So when you have like something like a scalar, which is just like a nice way to say like a number, right? It's just a number, so there's no specification either, right? So in a sense, like a scalar has zero indices, right? So it's just, you never like, you know, since it has no indices, like you don't refer to it in that way, you know, but it's kind of like a generalization of a special case in a sense. No indices. And then, you know, comes the matrix, right? And then the matrix, you have like the matrix A, you would say like something like A11, A12, right, up to A1n, and then AM1, AM2, up to AMN, right? So like the way I'm writing it, I'm thinking about it as being as M by N matrix, right? So this is M by N. Oh, yeah, actually, yeah. Right. And so here right, I guess, and by the way, stop me if like any of the notation, you know, doesn't look familiar or whatever. But like, so here, like you would refer to the entries of the matrix, right? Or like the components, if you like, as A sub ij, right? And so the idea is like the matrix has two indices, right? So the index I runs from 1 to M, right? The number of like rows, and the index J runs from 1 to N. Right, so from again, like, it's very down to earth perspective, like a matrix is just something that collection of numbers that you conveniently organize in terms of two indices, right? Like, you know, uh, and you know, you can kind of like see where I'm headed, you know. So 0 indices, 1 index, 2 indices. So again, like the next step would be something like that would require 3 indices, right? So what do we have my eraser? So and at this point, you have a decision, right? Because everyone is so far is being given like its own special name, scalar, vector, matrices. You don't want to keep doing this forever, right? So you just like generically refer to what's next as a tensor, right? If you wanted to be a little bit more specific, you could say like an order 3 tensor. Like so, for example, here is like an order 3 tensor, right? I'll use a letter T just for tensor. And then you would say, okay, again, if you wanted to think about it like visually, still we can kind of like do a little bit of that because you can think of it as like a collection of numbers arranged in kind of like a box type thing, right? Or so, well, I won't try to kind of like draw something super specific, you know, but right. And then like, you know, like the index I, you know, not that we're going to use this geometric representation too often, but you know, it's kind of like good to see it at least once. Like I goes down, moves down, like just as before. J moves to the right. And then if you wanted, you could do K kind of like some sort of depth into going into the board, you know, and then you kind of like with K going like moving this way, right? And then from that perspective, then then like you know, it's kind of like the Excel spreadsheet kind of thing, you know, like where you have like this grid, and then kind of like the tensor is kind of like the entries of the tensor, you know, like maybe this is kind of like entry, you know. Okay, so like maybe you go down to the second row, and then 1, 2, 3, 4. Okay, so this is like the fourth column, Okay, and then you are like a depth one, maybe, and so this would, well, I guess this would, like, yeah, like, oh no, this would be like one page besides it. Okay, so yeah, because maybe think of this as being behind the other one. Although here you see why you don't want to kind of like to do the picture too much, because now I'm getting confused. So, but it's kind of like the idea is like the entries of the tensor, are like you would just call them T, I, J, K or something like that, right? So like, it's like a collection of numbers. Um, that like they would store some information about like some data. But and there are many easy examples that you could come up with, you know, like for what an order 3 tensor could be. So here's like an example. So for like, well, let's start with, and by the way, under this notation, like a matrix is just like an order 2 tensor, right? Like if you wanted to go backwards, then like a matrix is order 2. Vector is order 1 tensor, right? And then like a scalar would be like an order 0 tensor, right? Scalar would be order 0. Okay, that makes sense. That's good. So okay, so like it's very easy to come up with like what you would like to call like a tensor. So actually just going back you know, to like the matrix example. You could have like an image, like you could have like an image which is, let's say, in black and white, right? So and so to store the image, then you could like kind of like imagine like the decomposition, like I don't know, into some sort of like pixels, you know, and then I guess like do you like the convention for I and J. This is I, this is J, and then to a particular pixel, you'll I don't know like associate like a number between 0 and 1. So let's say here's like a number. No, what is that? Let's use W. So like a W, or I for intensity. Oh no, like think you can confused with the index. Uh, okay, so it's so difficult to come up with a name for a number. So let's say C for color. So C is like the color of this pixel. Or maybe you have like some sort of like majority rule where like, maybe this pixel has some black and white. And if it's overwhelmingly black, you just declare it black. Or you can do it kind of like as a, you know, like being like a number, I don't know, 0 and 1, where like this would be completely white. And then this is completely black, right? And then, and then like that would be kind of like a way to store the image in terms of like a matrix, and then like kind of like so this is still would be like kind of like an order 2 tensor, right? Because it has two indices, and then the entry, the component just tells you like the intensity of the color. But then if you have like some sort of like simulation like of this room, actually you kind of like break it into mini cubes, mini boxes, and then there you go like with your order 3 tensor, right? So like like here, like I don't even have to draw the picture again. Like you could imagine this representing like a room, and then like the color or like the intensity of black and white would like that would be an order 3 tensor in a like natural way. Another one is kind of like kind of like the Netflix recommendation algorithms. Like you could have something like where like in one row you have like the users, right? Like so maybe you have listed all the subscribers to Netflix in some order, right? Like the other row, you know, you have like the movies themselves, right? So like this could be the subscribers or the like the users of like the product. It would be like the movies. And then like, just to have like an extra direction, um, you could have like if you ask everyone to give you like a ranking to the movie, so you could have a third direction that gives you how many stars like you you assign to the movie, right? In like with the understanding that maybe if you didn't watch it, you just like assign it as zero stars, and then like an entry in this box, an entry in this box could be like the amount of time that the user spent watching the movie just to see something done, like so like it could be like the amount of time watching the movie, because maybe like some people probably watch it again, right? So you could try to find like correlations between the number of stars you gave it and whether you watch it more than once or maybe the ones you gave it at 1 star, like stop after 20 minutes, and like maybe the time is like a useful piece of data to understand to have. But again, this is kind of like nicely organized as a tensor like of order three. And if there were more like aspects of it that you're interested in, then the order would increase, right? Like, in addition to time, there could be other things that you want to consider. And these, like, for example, this sort of tensor would be one that you would call like sparse, in the sense that you would expect the majority of the entries to be zero, right? Because like if you think about it, like a human, like how many movies, even if they were like addicted to movies, like they probably wouldn't watch that many, right? So like the majority of the entries would have zeros naturally because there's no ranking that you could give to them. So like this like something like this would be like kind of like a sparse tensor where like most entries are zero. Um, and like the idea is like if something like that happens, like you may want to like compress the data or like represent the data in a more convenient way, which is not keeping track of like every single entry of the tensor because like most of the entries are zero. So like, why would you do that? Is that making sense? If for example, the idea is like kind of like this suggests like one of the things that you want to do because like just to it's always fun to count parameters or entries, right? So again, like if you have like an order one tensor, as I was saying, that's just like a vector, right? So that has like n entries. Let's say like everything is kind of like squared. So like if you have like a square matrix, right? Like an order to that would be like n squared, and then order three, like again, like if it were cubical, again, like a cube, right? Like where like like the indices take the same number of values, like they all go from 1 to n, for example. And tensor, then n cube, and then like an order d, like let's say the order d tensor. A cubical, in the sense like all the indices take the same number of values, and it would be kind of like n to the d. So like the idea is like this, if you wanted to store all the entries, that kind of like um grows quickly with the dimension or like that, sometimes that's called like the curse of dimensionality because like, it just like like realistically after like a certain number for D, like you can like keep track of all the entries. So this is kind of like grow fast. So kind of like in a sense, like one of the points of like a tensor network, as you and we'll see about how that works, like in subsequent classes, is how do you present like a tensor in a way that captures some of the relevant information of the tensor, but without keeping track of every single entry, because like we kind of like agree that that's not realistic once you make the number like that order of the tensor large enough. So So like the goal is kind of like in a way to keep track of of interesting properties of the tensor or interesting features, let's just call it like that. Without you know, like storing, let's just use that word, without storing or like every single entry. Like so it's kind of like some sort of like compression method, you know. So you want to compress the data in some way that's useful. Okay, is that making sense about that? Okay, so now what I'm going to do, like the nice thing about doing it this way, I still haven't said what a tensor network is, but the nice thing about doing it this way is that it's very visual, you know, so it kind of gives you like a more visual understanding of certain features. So let me do kind of like I'll now go to a more mathy example. So I kind of will give you kind of like an idea of how the visualization works. And you'll see that's kind of like very convenient. So here's like a more mathy example. Which you can think of as coming from like the Taylor expansion of a function of two variables. So just to make it somewhat concrete, like let's think about the Taylor. So maybe just to let's do 1D, one dimension first, like a function of one variable, right? So what could be like what was kind of like the Taylor expansion or a function of one variable, just to you know just to not have like super annoying notation, you know, like say you want to do the expansion about the origin just because zero is like an easier number to work with, right? So if you remember f of x would be like f of zero, you know, plus f prime of zero times x, right? Plus 1/2 f double prime of zero times x squared, right? And then what, like 1/6, like, right, like 3 factorial, right? That's actually what you would like to say, but that's 1/6. Now, f triple prime of zero x cubed, blah, 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 right? Um, so that's kind of how it looks like for a function of one variable. And again, like you can do the expansion about any point, but if you just do it with zero, then you don't have to be putting x minus a squared, where a is like the point where you expand about. So it just kind of like saves your notation a little bit. Now, if you had a function of two variables, right? You can kind of like try something like that, analogous to this. So let me kind of like, but there will be way more terms that show up, right? So for example, like analogously, you would have like f of 0, 0, right? If you kind of like expand about the origin. Okay, so this is kind of like the zero order term, right? Then comes like a linear term, right? But now the linear term, like it was first derivatives, now there are two first derivatives, right? Because like there are two partial derivatives. So like let me just put it one level below so that it's kind of like not like kind of what we identify the levels more nicely. By this, I just mean that you evaluated the origin, like you know. So right, that is a linear term, right? And then sorry, I should put here like you evaluated the origin. So wait, I'll just do like that zero like arrow like that. And then okay, that would be the linear term. Then comes a quadratic term, right? Okay. Okay, so you would imagine like x, right? Should go with x squared. Then you would think that like y should go with y squared. And again, like they are like all evaluated at 0. Okay. And then, uh, okay, so then comes like the mixed terms, right, which are like the fun ones. Uh, right? Which, if you remember from Calc 3, because again, I think most of you took it, it doesn't matter like the mixed partial derivatives, again, like the beauty of it is like, it doesn't matter in which order you take them. So actually you can recombine if you wanted these as 2 times one of, like they are really like the same term. But if you for some reason didn't know that they were the same, that's actually how you would express them, right? So like this would be, this because of like the commutativity, that the mixed partial derivatives commute, you can rearrange this as 2 times, right? Whichever you prefer to write it as. Yeah, that could be like one way to write it. So far, so good. Everyone with me? Making sense. And then, okay, so now here's where I want to show you like the advantage of like the tensor stuff. Then you could ask, what comes next, right? So what should be like the third order? Like, there should be kind of like a cubic thing that comes next, right? Right. And I could, yes.
Why isn't the XY squared?
Uh, you're talking about here like F1. Well, I mean, it's that, well, maybe like think about it like first, like why is like x squared here, right? Because you're doing x and then x, right? So, and they're like supposed to be quadratic, right? So it makes sense that if you're doing x twice, that should go with x squared. Here you're doing y twice, so just that should go with y squared. But then here you're doing x and then y, so that should go with x times y, and similarly with the other. Is that making sense?
Yeah.
So it's kind of like, because like if you think of the derivatives kind of like as a direction, like in which you're differentiating, like you should kind of like keep track of that with like the corresponding variable that does it. So now I could spit out the formula for the cubic one, but it would look so much messier, right? So we want to kind of like have like a more like visual understanding for where the formula comes from, right? And this is kind of like a good like example where like I can start introducing a little bit of like this tensor visual notation, like or diagrammatic notation. So here's like so like we'll figure out what the cubic contribution should be just from diagrams. Okay. So let's just use pictures to figure out the cubic pair. Just pictures. Okay. So okay, so the idea, like what I'll do is first kind of like reinterpret each of these levels in terms of a picture. Okay, so and this is now again like a good idea of like introduction for how the tensor diagrams work. But the idea is that if you just have a number, right, because this is like a scalar, it's like this is just like a scalar. So in the tensor representation, this is 0 order, right? So this is just drawn as a circle or like a node, if you want to call it like that. So this I would just call like f0. So this would be kind of like as a picture, like the way I would represent this number is just by drawing a circle, like, and I'll put the name of the circle just being like f0. So like a scalar would always be just like a circle. Okay. Now, the linear term, now here gets a little bit more interesting. Right. The linear term, of course, this is like also like a number, right? Like this is a number, but it's a number that you can interpret as a dot product. It's a number that is a dot product of 2 vectors. So there are 2 vectors hidden in this picture. One vector is the gradient. Okay, so let's just rewrite this. Like there there was a gradient vector, right? Which, like, just to make a more uniform notation, I'll write it like this. So by this, I just mean like the first entry of the gradient vector, the second entry of the gradient vector. So like I'll use like a subscript to refer to the entries. Okay, if you wanted to represent this as a diagram, okay, and again, maybe I should put this here, like that this is order 0. Okay. The gradient is a vector. So as we were saying before, like it has one index, right? Like the index here, like this first entry, second entry. So it's like an order 1 tensor, right? Order 1 tensor. So in this tensor notation, like whenever you have a vector, you draw it as a circle. As a circle with like one kind of like edge coming out of it, or like a node with one edge like coming out of it. So like this will be the way to represent the vector. So the idea is that it has like one edge coming out of it because it's order 1. And like this may be less important right now, but I'm just calling the edge I because that refers to like the index that I'll use for the vector. Okay. By the way, for now, it doesn't matter whether the edge points right, up, down, left. You could put it anywhere you want it. Then later you can do like a tiny subtle distinction between whether it goes right or left, which involves something called the dual of a vector. But like that is not important for now because again, we're kind of like doing the down to earth version. So you just drive wherever you want. Okay. So that is one of the vectors involved. The other vector that's involved is xy, right? Like the position. Like so, the other vector here was. Which again, I'll kind of like refer to it as x1, x2, just to kind of uniform, make a more uniform notation. Okay, and this is another vector. And then it has like entries up, like the index is I for this guy. Okay. So again, like scalars have like 0 outgoing edges in a sense, and like a vector, for example, is represented in this way with anything that has like one outgoing edge. Okay. And then kind of like the cute thing to represent this operation is that like just imagine that you kind of like bring them together and merge the edges. So kind of like the idea is that, and this will be called like a contraction, is that again, like, because it doesn't matter how you look at the edges, just imagine like, almost like it's like some sort of like marriage, right? So you kind of bring them together. And then the rule, again, like this operation is called the contraction. The idea is like this entity has a kind of like no open edges, right? Because they're all connected now to one another. And the way this is supposed to go as like, is that this will produce a scalar, which is obtained by summing over I of like the entries of the vector times the entries of the other vector. So by this, like just to kind of make it more clear, by this I just mean first entry times first entry plus second entry times second entry. So this would be first entry of the gradient times first entry of the position vector plus second entry of the gradient times second entry of the position vector. Okay. Yes.
So like you take through like the vectors and we put them in a contradiction.
A contraction.
Contraction. It goes into the scale.
Yes, if it's only two vectors, right, like it will correspond to a scalar, yes. Yes, correct. Okay, now here comes a cute thing. So okay, so this is the order 0, order 1. If you just follow the logic, the next one should have been order 2. So if it's order 2, the idea is that secretly there should have been like an order 2 tensor hidden in this formula. Order 2 tensor is a matrix. So secretly there should have been a matrix in this formula. The matrix is going to be derivative with respect to x squared, derivative with respect to y squared, and and then x and xy, which is what you would have called like the Hessian if you saw it under that name in Calc 3. So in order to, and this is where like things get tough. So in degree 2, this formula is order 2. So I'll create like a tensor, which I'll call H, because like again, that's called like the Hessian usually. This is like the one that appears on the second derivative test when you're classifying critical points. So this would be. And again, this is like in the other notation, like more uniform notation would be H11, H12, H21, H22, right? Asymmetric matrix, right? So it's like the way you would write it is like H12 is H21. But more generally, like like obviously with 1 and 2, like you can also like permute them and interchange them, and there's no difference. So like the way in which you typically just write this property is that Hij is the same as Hji, and that's called like the symmetric property of the matrix. Okay, and because it has order 2, there should be 2 edges coming out of it. Okay, so if you want to represent this as a tensor, you should have 2 edges coming out of it. Okay, so that, and because it has 2 edges coming out of it, it's waiting for 2 things to merge with to produce a number, right? So you can kind of like see where this goes, right? Because if you insert an x vector from each side, right? So if you do, like, let's just put it here, like, I'm using the x vector with, if you merge it with I, and then the other one is j. The only thing that you have to be, cognizant, conscientious about is that they should have like the same name for the label. So if I calling them I and I here, you should call these J and J. So like that's fine because you can always like it's kind of like a when you integrate where like it doesn't matter like the name that you use for the variable of integration. It's kind of like what people call like as a dummy index. So you can call it whatever you need it to be. Okay. And so kind of like the way this is supposed to go is that you're kind of merging along this along this edge, merging along this other edge. So there are no like free edges, all have been contracted. So that should spit out a scalar, and the scalar that corresponds to would be this one. Okay. So kind of like, but this is like so much more like transparent explanation of what's going on instead of like writing it all down, like, like entry by entry, you'll see why in the next one. But, so what this corresponds to is kind of like a massive sum over I and J, so like kind of like sum I from, and sum over I, sum over J, like these entries like Xi. Well, I mean, like what's happening here is like, they can kind of like contract these two first, then you are left with like a vector, and then you contract it with the other one. But it kind of like ends up being equivalent to what I just wrote. So you kind of like do all the possible products. Like that's kind of like the way to think about it. You multiply this entry with this one and this entry with this other, and then you sum over like the I and J's. So that it will give you like, if you just start giving values to I and J, you start with 1, so you do x1, h11, x1 plus x1, h12, x2 plus what x2, two, one, x1 plus x2, h2, two, x2. And you kind of like check, you can check that that kind of like corresponds to exactly the same expression that we had written down a bit earlier. Okay.
Give me the figures all that's a little matrix multiplication.
Well, it is okay, right? And you just have to be careful because, like, if you wanted to write it as a matrix multiplication, this is what corresponds to this formula. If you think of the vector as being a column vector, because the matrix is 2 by 2, right? This is being a column vector, this will be 2 by 1. And then when you transpose it, right, like it becomes 1 by 2. So that guarantees that everything can be worked out. So yes, it does give the matrix, it does correspond to a matrix multiplication, but you do have to remember to transpose one of them. And that actually is related to the fact that one, I had to make one point to the left and the other one to the right. So I was saying right now, like, for now, I'm not kind of like paying too much attention for like in which direction the indices are pointing, but the idea is like, again, we'll talk about that later. That's kind of like the distinction between like a bra and a ket, like in quantum mechanics, like, like one is like a column vector, the other is a row vector, and then the contraction like just is multiplication, if you keep that in mind. And this is called, like, again, like terminology that I'll throw in later. This would be kind of like called like a bilinear form, like the matrix itself. Yeah.
So the way I'm conceptualizing the whole of this diagram is that every one of the links essentially is just representing sort of the for loop.
Yeah.
The more links we have in combination, you just have more for loops stacked.
Right.
Each one.
Yes. Actually, let's do the third one, like, because then that makes it clear, like, yeah, like the cubic term, right? But like, will be kind of like the same idea, but then it will have three edges coming out of it, right? So you kind of like stack it with three vectors so that this works. So here in like just like to finish at least the cubic one so that you see why this is useful, because now you kind of come up with the formula just by analogy. You kind of like convince yourself, oh, this is kind of like working. So let's try to see what should the cubic term be. So for the cubic term, there should be kind of like a tensor of the order 3. So there should be an order 3 tensor. Which is kind of like by analogy. Okay, so if you think about it, like, let's just put the order 1 here. The order 1 tensor was the gradient. So the order 1 involves first partial derivatives, the order 2 involves second partial derivatives, so order 3 should involve third partial derivatives. So the entries of this tensor, right, which again would be some sort of box, but I don't want to draw the box anymore. The entries of this tensor should be the third partial derivative of the function with respect to xi, xj, and xk. Okay. Or here I can be 1 or 2, 1 or 2. I, j, and k can both be 1 or 2 each. So I is 1 or 2, j is 1 or 2, and k is 1 or 2. So just to give you like a great example, if you chose like d1, 2, 1, this like the entry, like that entry corresponds to the third partial derivative of f with respect to x1, with respect to x2, with respect to x1. Right, but x1 is x and x2 is y, and again, it doesn't matter in which order you take partial derivatives, so it's only twice with respect to x and once with respect to y. So like the entry of this tensor should be something like that. So it's kind of like a vector that takes into account all the tensor. This tensor, its entries are all the possible ways in which you can take the third partial derivative of the function. Some of the entries would be the same, right? Because it doesn't matter in which order you take the partial derivatives, in the same way in which here this entry and this entry are the same, right? So it's what you would call like a totally symmetric tensor, if someone wants like the terminology, because the idea is like this should be the same entry as T2, 1, 1, or the same as the entry, T112, like they should all be the same entry because here, like it only matters how many times you did the derivative with respect to one of the variables. So in all of these cases, it is being done twice with respect to X and once with respect to Y, and that's all that you care about. Okay. So they all would be the same. Like in this box, those entries all like agree with one another. Okay. And then the beauty is like, just if you continue with this, it's like, oh, okay, so what this should have been. So because this is order 3, it kind of has 3 outgoing edges coming out of it. Again, you don't have to draw them in any particular order right now. And then you can contract it with 3 things, right? So you contract it with X, the X vector 3 times. Oops. And again, because you kind of close off all, sorry, yes.
You also like track it with like matrix X and scalar X.
Oh yeah, you can do like right. Not for this formula, right? For it to come correctly, but yeah, like if you have like a, just to put it as an aside, if you had a tensor, right, because it has 3 edges, right? Like you could take a matrix, right, which has 2 edges. You contract here. If you don't want to contract anymore, then there's only one edge left, so that would be a vector, right? Because there's only one remaining edge. And if you wanted to produce a number, kind of, which is what we're doing right now, you close it off with a with a vector. But that's just kind of like the flexibility of the diagrams, because then you can start thinking about, let's do crazy things. Also, another thing you could do, is that if you had like an order 3 tensor, right? If you had like an order 3 tensor, then you could also close it off with an order 3 tensor because they all have 3 edges, right? So you can. And again, if the projector were working, then I would show you like very cool pictures of all of this stuff. Yeah.
So is it basically just like adding inputs together to make a tensor that's the same size, like more like a multiplication on basically?
It is kind of like a generalization of the multiplication, right? Like between matrices or like vector with matrix. Yeah. So you just have to make sure that they match along the common edge, right? Which is kind of like how matrices works, right? Because to multiply edges and matrices, right? When you have like the matrix A times B, right? You needed, if this was n by n, you needed the other one to start with n here, so that it closes it off to be. So yeah, this tensor contraction is just a natural extension of matrix multiplication, like multiplication between matrices or between vectors and matrices and all this stuff.
So the n and t in the same and a is the same as n, a in the same.
Correct, right? I'm forcing it on the diagram itself because I'm already calling them like k and k. Yeah. So yeah, exactly. Well, actually, yeah, like I mean, I'll probably put those as exercises, but yeah, exactly. Like the idea is like if you had like a matrix, and you have like a vector, this is kind of like a diagram that represents like the vector A times V because and so on. You could kind of like start playing with translating the matrix equations into tensor notation, which I'll put like some of those as problems for you to work on because they're kind of like fun to just go through the details, but it kind of like makes it kind of like super clear that they should be a vector because there's only one edge remaining. And that's kind of like the idea. Whereas if you write all of this in a humongous sum notation, like, you kind of like get lost in the weeds of what's going on. But like these, like, and like in tensor networks, then you have like super cool things, like, things like this. And things of that other sort, which are like tensor trains, and they have their own names. But like it's kind of like a contraction of a bunch of different tensors, and that's why it's called like a network, because literally you start seeing like kind of like this, like web of like nodes and edges, like all these contractions taking place and all this other stuff. So, but yeah, it's kind of like it's always fun when you can diagramize things. So kind of like the idea here, just to write it down. And that's good. That can be the kind of like the last thing I did today, actually. Sorry, what's one? Oh, okay. So the idea is that this thing would correspond again to a humongous sum, like I, j, and k of t, I, j, k, like xi, xk, xk. These are numbers. Since they're all numbers, it doesn't matter in which order you write them, right? And this is actually, if you ever take general relativity, like this is kind of like also like related to Einstein's sum, like tensors, like in general relativity, they usually don't write the sum notation explicitly. So they're like the Einstein convention is like whenever an index is repeated, you just implicitly sum over it. So like, like a way, which I won't do. I will always write the sum if needed. But like a way of physics usually writes that down. It's just like this, and they understand that if you have repeated indices, you just sum. Like so, this is sometimes called like the Einstein summation convention. The thing is like there's a little bit more tricky because for now there's like a distinction between upper and lower indices that I'm not getting into right now, but it's kind of like the same idea. And then here, like, but this kind of like gives you the cubic term in Taylor. So this would be kind of like T111 x1 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 plus T112 x1 x1 x2. Okay. Plus, and it's kind of like a combinatorics problem, right? Like, you just have to start choosing like different values for 1 and 2 for each entry. So you have like what T21 x1 x2 x1. Okay. And then well, actually, let me rewrite them in a way that's a little bit more clear. So this is like that at this level is where 1 appears 3 times. Then you want 1 to appear twice, right? So you would do T112 x1 x1 x2 plus T121 x1 x2 x1, and then plus T211 x2 x1 x1, right? So like at this level, 1 appears twice, then 1 should appear once, right? So it's T122 x1 x2 x2 plus T212 x2 x1 x2 plus T221, right? I'm moving the 1, yes, x2 x2 x1, and last 2 appears 3 times, right? So 1 appears 0 times. Like so, I kind of yeah, that's nicer to organize this way. So T2 x2 x2 x2. Okay. And now you see what people never like, this is why you use the sum notation, because you do want to avoid writing these things out explicitly, but it's kind of like nice the first time to kind of like see it written down somewhere. So if you simplify all of this, this just means x1 was x. So it means like the third partial derivative with respect to x, right? Times x cubed. And then these are all the same, right? Because again, it's x1 squared times x2, and like it doesn't like the mixed partial derivatives commute. So it ends up becoming 3 times, the third partial derivative once with respect to x, twice with respect to x, and once with respect to y of x squared y, right? Then comes like the similar here, like these 3 terms are actually the same. That's because like tensor is symmetric. So 3 times the third partial derivative with respect to x, and then twice with respect to y, xy squared, and the last one is like 3 times with respect to y. Okay, and that is in the Taylor expansion is that thing times 1/6, right? Because you have to multiply by 1/3 factorial. That would be the cubic term in the Taylor expansion. The thing is like you can kind of like see this generalizes to any number of variables. You know how to continue for any order, like so once you understand how this is supposed to work, you can kind of like you see like the like what the answer should be without having the need to write it down explicitly. Yeah.
So essentially what we've done is define products of tensors, but the way we have matrix products, now we have generalized products.
Yeah, it's like yeah. Like it's kind of like a tensor. Yeah. Like this, you could like a contraction. You can think of it as some sort of tensor product. Yes. Because like in the case of matrices, like the contraction is like the matrix multiplication. So yes, this is kind of like a tensor multiplication. But it's usually the word contraction is called used because sometimes as we were in the diagrams I was doing, sometimes you just choose to contract some of the edges and not all of them and leave some kind of like on their own. Like kind of like the idea of like this is that there's a lot of flexibility on how you want to do the contraction. In fact, it is similar. Yeah, we actually will talk about that later. I don't know, like you could have like 6 matrices, right? Like you're multiplying, and to multiply the matrices, you kind of like multiply 2 first, and then what you get with the other one, like there are different ways, like like the matrix multiplication, you can definitely you cannot swap the order, right? Because matrix multiplication does depend on the order, but you could like, for example, multiply these 2 first, multiply these 2 first, and these two, and then whatever you get, you multiply together and so on. So there are different ways in which you can do the multiplication between matrices, but actually some of them are more efficient than others in terms of computational time. So it's like not that they do take the same amount of time. We'll do like some examples about that later on. So similarly here, when you contract tensors, if it has like 100 edges, like or you have one of these tensor networks, if you have something like this, is definitely going to be a scalar, right? Like there are no free edges, everything has been contracted, but you could kind of like decide, oh, let me merge these 2 first, or let me merge these 2 first, or like these 2 first. I mean, but there's kind of like a better ways of merging the edges together that would take you less amount of operations, arithmetic operations like multiplication and stuff like that. So like there are some efficiency questions that you have to keep in mind, but yeah, like kind of like these kind of like represents like some sort of generalization of like matrix multiplication. That's correct. Is that making sense? Yeah.
We'll probably even talk about how this works during the course, but what does it mean to like evaluate patterns in our since doesn't everything depend on basically like everything else?
Well, I mean, so what that means is like, no, like that's where you have to decide to leave certain indices open. Right, right. Like if you close everything up, you get like a number, and there everything does depend on everything else, as you're saying. But like for example, like and could be like like a good way, a good place to end. So like just like in the most basic thing that I was saying with matrices and like vectors, if you have like a matrix, right? Imagine you have like a matrix and a vector, right? If I choose just to leave one open, right? Because I choose to leave one open, whatever this produces is a vector, right? So this vector I'll call W, right? Like this is a vector W, which has entries, right? So the entries are W sub I, right? So this vector has entries Wi. So for example, if you wanted the first entry of the network, right, of this vector, what is the W1, the first entry of this vector? It is, 1, A, then J, and D, right? So that means that you sum over the J's, but you did leave the I fixed. So this would correspond to like the sum over J of A, 1J, DJ, right? And those are really like the entries for like the matrix. Like this is like the ith entry of A times B. So you see, if you close everything up, then there's no freedom and everything depends on one another. But it is kind of like a way to search for like a particular entry of the vector, like in this case, because you kind of like, okay, you are just maybe interested for whatever is in the first entry, and so you just have to do this operation, So that is like a way, it's kind of like a storage thing, because that way, if you don't want to see all the entries, then you can just like, you always can evaluate. You can give a particular value of the index to the free ones. Like, like the indices, there's some that are free and the others are kind of like constrained. Sometimes these are called virtual bonds, like because it's kind of by analogy with condensed matter physics. So these are kind of like, they're not really out there because they're being summed over. So you have no freedom on what value to give to them because they all have to be summed over all the possible values. But the ones that you leave free, then you can choose your favorite value for them. And that's how you generate different entries of the vector, the tensor, if that makes sense. Yeah, but it takes some time to get used to that idea, but we'll get there eventually, if that answers your question.
So did the matrix multiplication formula come from the generalization? The generalization?
Oh, no, like, I mean, this is kind of like a more decades old thing, so like, in fact, like even the vector notation, like, with the dot product and the cross product, it comes later after like the formulas were figured out. Like, so someone realized that you could like use like the vector notation to kind of like simplify things out. But yeah, so like kind of like this comes after the fact that you had like all the algebraic formulas, and then like you kind of like this is sometimes called Penrose notation because he was one of the people who worked on this, although it had been like an idea around for some time. But the idea is like, yeah, like how do like the visual representation did like arrive like later on. Actually, maybe but it kind of like takes a life of its own. That's kind of like you should think about it, Sorry, would you want to say something?
So where's the general form of matrix multiplication exist?
Yeah. Oh, yeah. Like, in fact, in general relativity, again, like this thing is just contraction, and this was like, Riemann, like, in general relativity, this is all related to the Riemann curvature tensor and all this other stuff. Is that you would just write it like with massive sum, like, it was all very algebraically written. Like they wouldn't represent it in this way. Here's, for example, a really cool one. If you want to work it out, I'll add it as an assignment problem just because it's fun. Okay, so like again, like this should be like you have two matrices, you multiply them, but what if you close it up, right? Then that should give you like a number, right? So you should try to work out what the number is. Like just try it in the 2x2 case and like see if you find. I don't want to spill out the answer, right? Because it's a kind of fun exercise to do. But if you call this like common index I and this common index, sorry, if you call this index shared J and this other one I, you just write the sum and see if you find something that you recognize. And it's actually like an important quantity involving the two matrices. But think about it like, if you want, I'll add it as a problem for you to figure out. But at least in the 2x2 case, you can kind of like write everything very explicitly and see if you recognize something, familiar. Okay, so let's finish here and then I'll try to fix the projector for next time so that we can kind of like, I can write on the iPad because that'd be convenient so that way you keep like the notes. But I think this is a good place to end.